A hollow eggshell weighs almost nothing, but for Keith Thomas, lifting one required a 15-hour brain surgery, 5 implanted electrode arrays, 2 artificial neural networks, electrical stimulation of his spinal cord, and a custom robotic brace attached to his hand. Thomas could not see the eggshell. He could not see his fingers. After a spinal cord injury, he had almost no sensation in his hand and no voluntary control of his fingers. He simply imagined closing them.
Signals from 10 carefully selected electrodes inside his motor cortex entered a computer. A neural network decoded his intention. Electrical pulses activated muscles in his forearm, and artificial tendons inside a 3-dimensional printed brace closed his fingers around the shell. Then, a second artificial intelligence system took control of the pressure. Without this system, Thomas successfully regulated his grip in only 27% of the trials. With it, his success rate jumped to 87%. Pressure sensors also sent information in the opposite direction, directly into the sensory cortex of his brain. When this artificial sense of touch was active, Thomas identified whether the eggshell was inside his hand with 100% accuracy. Without sensory feedback, his performance fell to chance level. These numbers come from a Nature Medicine study published on July 16, 2026. The research was led by Santosh Chandrasekaran, Sarah Wandelt, and bioelectronic medicine researcher Chad Boughton, working with a team of engineers, neuroscientists, therapists, and neurosurgeon Ashish Mehta. Their system did more than temporarily move a paralyzed hand. Some improvements remained after the equipment was turned off. According to Bhutan, we're not just bypassing the injury, we're actually rewiring the nervous system. That claim sounds almost impossible. The study involved only one participant, so it is not proof that paralysis has been cured. Yet the measured results were significant. Strength in Thomas's arms rose for months. Sensation returned to part of his wrist, and those sensory gains persisted for more than 2 months after stimulation ended. The technology is called a double neural bypass. To understand why it matters, we first need to understand exactly what happened to Keith Thomas. In July of 2020, Thomas dove into a swimming pool, struck his head, and broke his neck. The accident damaged his spinal cord at approximately the 4th and 5th cervical levels. When researchers enrolled him 13 months later, he had what the Nature Medicine authors classified as complete C4 sensory and C5 motor tetraplegia. He could barely lift his arms from the armrests of his wheelchair. He could not bring his hands to his face, hold ordinary objects, voluntarily move his fingers, or feel touch in his hands and wrists. His brain still knew how to move. His muscles had not completely disappeared. The connection between them had been severely interrupted. According to the World Health Organization, roughly 15.4 million people were living with spinal cord injuries in 2021. More than half of spinal cord injury cases involving paralysis include some degree of tetraplegia, according to the Nature Medicine paper. For many of these patients, restoring hand and arm function is the highest priority. Walking receives more public attention, but the ability to eat, drink, wash, dress, or use a phone can determine whether a person needs constant assistance. Researchers were not attempting to regrow Thomas's damaged spinal cord. Their immediate goal was more mechanical: build a digital route around the injury. Before surgery, the team used functional magnetic resonance imaging to identify the regions of Thomas's brain associated with attempted finger movement and imagined touch. In March of 2023, Ashish Mehta and his surgical team performed an operation lasting approximately 15 hours. 5 microelectrode arrays were placed in Thomas's left cerebral hemisphere. 2 arrays entered the primary motor cortex, which produces movement commands. 3 entered the primary somatosensory cortex, which processes touch. Together, the arrays contained 224 electrode channels,
128 in the motor cortex, and 96 in the sensory cortex.
During part of the surgery, Thomas was awake. Mehta stimulated individual areas of the exposed cortex while Thomas described what he felt. The team identified locations connected to his thumb, index finger, middle finger, and pinky. Thomas had not experienced normal sensation in those fingers for nearly 3 years. When stimulation produced a feeling again, he later told Time magazine, "It's indescribable to be able to feel something." The implants did not magically restore movement. They produced electrical data that first had to be translated. When Thomas watched a virtual hand open and close, he imagined and attempted to perform the same movements. His physical fingers remained still, but neurons in the motor cortex changed their activity. The researchers recorded frequencies between 100 and 5,000 Hz every 100 milliseconds. They then trained a long short-term memory neural network, commonly called an LSTM, to distinguish between rest, opening the hand, closing it, and reaching. Although the motor implants contained 128 channels, the final decoder used information from only 10 electrodes. Those 10 were selected because their signals remained consistent across more than 80% of the training sessions. The model was trained using 20 blocks of data collected during 6 sessions over 16 days. After training, the researchers locked the decoder and stopped retraining it. 5 months later, the same model was still working. Its best movement classification accuracy reached 84.6%. That stability matters because signals from invasive brain implants often change over time. A system that must be recalibrated every morning would be difficult to use outside a laboratory. Here, a small group of 10 electrodes remained reliable enough to decode 4 movement states for months. Once the computer recognized Thomas's intention, it sent commands to neuromuscular stimulation pads on his forearm. Electrical current activated muscles responsible for opening and closing the hand. Some muscles responded, but several finger flexors remained too weak because Thomas also appeared to have damage to lower motor neurons. The team solved this problem with a low-profile active orthosis produced using 3-dimensional printing. Artificial tendons in the brace helped bend his index and middle fingers. Thomas's intention now traveled through an extraordinary chain. Electrical activity began in his biological motor cortex, crossed into an artificial neural network, became a digital command, activated an electrical muscle stimulator, and finally moved artificial tendons attached to his real fingers. This allowed Thomas to open and close his own hand, drink from a cup, bring food to his mouth, and hold his sister's hand. Movement alone, however, was not enough. Without touch, gripping an object becomes surprisingly difficult. A person must know whether the fingers have made contact, whether the object is slipping, and whether the hand is applying too much pressure. Chad Boughton explained the problem directly. "We can't even button our shirts without that tactile feedback." Earlier brain-computer interfaces had already demonstrated thought-controlled movement. In a 2016 Nature study, Boughton and colleagues connected signals from a man's motor cortex to electrical stimulation of his forearm muscles. The participant could pour liquid, swipe a credit card, and play a simple video game. That system restored movement, but not touch. Other groups later stimulated the sensory cortex while people controlled robotic arms. The brain could receive artificial tactile information from an external machine, but the loop did not fully connect a person's own paralyzed hand back to their own brain.
Thomas's system attempted both functions at once. Force sensors were placed in his palm and robotic brace. When his fingers contacted an object, the sensors measured pressure and triggered stimulation through multiple electrodes in the somatosensory cortex.
The resulting sensation was not identical to natural touch. Thomas described earlier versions as something closer to a burst of energy.
Even so, his brain could distinguish whether an object was present. The hollow eggshell experiment showed exactly why that mattered. The LSTM neural network detected when Thomas wanted to begin or end a grasp. However, activity in the motor cortex was strongest at the beginning and end of movement, making it unreliable for continuously regulating pressure. Researchers therefore added a deep reinforcement learning agent. The model was trained in a simulation, not through thousands of dangerous attempts with Thomas's hand. It received a digital reward for reaching the required pressure quickly and remaining below the force that could crush the shell. During 5 experimental sessions, the researchers compared 97 trials with the reinforcement learning controller against 85 trials without it. The success rate increased from 27 to 87%. The statistical probability that this difference occurred by chance was approximately 1.2%. Artificial intelligence was not deciding whether Thomas should pick up the object. His brain still initiated and terminated the grasp. The algorithm handled the continuous microcorrections that a healthy nervous system normally performs without conscious thought. Sensory feedback produced another dramatic result. Thomas was visually blocked from seeing both his hand and the eggshell. With stimulation of the sensory cortex turned on, he correctly recognized the presence of the shell in every tested block. When the stimulation was removed, he performed at approximately 50%, which was the expected result from random guessing. When the stimulation was removed, he performed at approximately 50%, which was the expected result from random guessing. Before beginning spinal stimulation, the team measured Thomas's arm strength for 20 weeks. This long baseline was designed to rule out delayed spontaneous recovery. Researchers then placed a custom electrode patch over the cervical region of his spinal cord. Depending on the target muscles, the patch stimulated nerve roots near C5 and C6, or lower roots near C7 and C8. The system delivered stimulation at 50 Hz, with current reaching as high as 300 milliamps during activity-based training. After 15 weeks, the force generated by Thomas's right biceps increased by 61%. His left increased by 25%. The raw measurements were equally clear. Median right elbow flexion rose from 13.25 newtons before stimulation to 21.32 newtons. On the left, it increased from 24.03 to 30.12 newtons. Improvement continued. After approximately 35 weeks, right side force was 86% above baseline, reaching 24.65 newtons. Left side force was 62% higher, reaching 38.9 newtons. Thomas could now bring both hands toward his face, even when the brain-controlled hand system was not operating. Spinal stimulation alone did not restore movement in his fingers or sensation in his hands. The researchers therefore created a second experimental method called cortical mirroring. They recorded patterns from the sensory cortex, while Thomas imagined being touched on his thumb, index finger, or wrist. Up to 16 electrodes showing the strongest and most consistent responses were selected during each session. Those cortical patterns were then replayed into his brain using stimulation at 200 Hz. At the same time, vibration was applied to the matching area of skin, while stimulation increased the excitability of circuits inside the spinal cord. Instead of sending one artificial touch signal, the system repeatedly synchronized the brain, spinal cord, and peripheral nerves. The intervention produced its clearest result at the right wrist. Before therapy, Thomas could not reliably detect touch there. During the intervention, he perceived pressure as low as approximately 10 grams. In another blinded experiment, researchers applied 700 grams of force to different locations. Across 11 sessions, Thomas correctly identified touch at his wrist with an average accuracy of 81%. The improvement remained measurable for more than 2 months after stimulation stopped. No comparable recovery appeared in the thumb pad or index fingertip, an important limitation that the authors clearly reported. The system did not restore normal sensation throughout the entire hand. Even so, Thomas began noticing changes outside the laboratory. He could scratch his face, wipe his eyes, and feel the fur of his dog against an area of his wrist that had previously been numb.
In a statement released with the final study, Thomas said the technology had restored experiences taken away by the injury. He added, "The technology has given me back both connection and sense of self." This is why the researchers use the term double neural bypass. One pathway provides immediate assistance. It reads movement intentions from the brain, activates muscles, controls a mechanical brace, and returns artificial touch. The second pathway is therapeutic. Repeated synchronized stimulation attempts to strengthen the biological circuits that survived the spinal injury. This distinction separates the system from a conventional brain-controlled prosthesis. A prosthesis usually works only while it is active. Here, the researchers measured gains in arm strength and wrist sensation after stimulation ended. The idea is not completely isolated.
In 2023, Henri Laurac, Jocelyn Bloch, Gregoire Courtine, and their colleagues reported a different brain-spine interface in Nature. Their system allowed a man with an incomplete spinal cord injury to stand, walk, climb stairs, and cross uneven terrain. That participant's walking interface remained stable for approximately 1 year, and rehabilitation improved his ability to walk even when the system was turned off. The Thomas study targeted a more severe, clinically complete injury and focused on the upper body. It also added artificial touch, direct muscle stimulation, a robotic hand brace, reinforcement learning, and patterned stimulation of the sensory cortex. However, the limitations are substantial. The Nature Medicine paper describes one participant. A result in one person cannot establish how well the system will work across different ages, injuries, or medical histories. Thomas required open brain surgery. Components still exit through pedestals mounted on the skull and connect to external computers. Electrodes must be placed on the skin, and the hand requires a custom brace because some muscles cannot produce sufficient force. The decoder recognized 4 broad states rather than natural control of every joint. Sensation improved mainly at the wrist, not across the fingertips. Daily use still depends on specialized equipment and trained researchers. Months of intensive rehabilitation may also explain part of the recovery. The researchers established a 20-week baseline and reported strong statistical changes, but a single participant study cannot completely separate every contributing factor. Boutin's team is planning expanded trials involving people with different levels of spinal cord injury. Until those trials reproduce the result, the phrase rewiring the nervous system should be treated as a promising interpretation, not a settled medical fact. Yet the measured achievement remains extraordinary. A man with clinically complete tetraplegia used signals from only 10 motor cortex electrodes to control his own hand with up to 84.6% decoding accuracy. Reinforcement learning increased precise grip control from 27 to 87%. Artificial sensory feedback raised object detection from chance level to 100%. Right arm strength eventually increased by 86%, left arm strength by 62%, and restored wrist sensation remained measurable for more than 2 months after stimulation ended. This is not a cure for paralysis. It is something more specific and, for now, more scientifically defensible. A digital system that can read intention from the brain, return touch to the brain, control the person's own muscles, and possibly train surviving neural pathways to become useful again. The first major human-machine breakthroughs may not give healthy people superhuman intelligence or perfect memory. They may give a paralyzed man something far more immediate. Enough control to lift a cup, enough precision to hold an eggshell, and enough sensation
to feel another person's hand.